When you write code to create a new object, the abstraction feels effortless, but beneath that command lies a volatile physical reality. To make software development possible, compilers construct a logical address space, a uniform, seemingly infinite environment where every variable appears neatly organized. This abstraction works perfectly for local variables, confined to a single function. But when a program creates dynamic data, objects that outlive the function that created them, it cannot be stored on the temporary stack. It must be housed in a dynamic pool of memory, known as the heap. Managing this dynamic pool requires an invisible subsystem called the memory manager, which serves as the strict interface between your application and the OS. The memory manager has two mandates. First, satisfy unpredictable allocation requests, ranging from bytes to gigabytes. Second, track and recycle memory the moment it's no longer needed. Executing these mandates forces the memory manager into a continuous dual optimization problem. It has to minimize spatial fragmentation to prevent the application from running out of room, while simultaneously maximizing physical data locality so the processor can actually read the data without stalling. To understand why data placement matters, we must look at a hard limitation in hardware engineering. System architects can build storage that is exceptionally fast, or storage that is exceptionally large. They cannot build storage that is both. This limitation dictates the memory hierarchy. The closer a storage tier sits to the processor core, the faster and smaller it becomes. This diagram maps the massive latency deltas across that hierarchy. A processor relies on its internal registers, measuring access times in a single nanosecond. Beneath that sit the L1 and L2 caches, running at 5 to 60 nanoseconds. Further down is the massive physical memory, running at 100 to 150 nanoseconds, backed entirely by virtual memory disks that take entire milliseconds to access. Data does not travel up this hierarchy one byte at a time. To amortize the massive cost of an access request, hardware moves data between main memory and the cache in fixed, contiguous structures called cache lines, typically ranging from 32 to 250 fixed bytes. If the processor requests data that is not in the cache, it triggers a cache miss. The core is forced to stall, waiting idly while the request travels orders of magnitude slower down to physical memory, pulls a new cache line, and returns it. Actual execution speed, therefore, relies directly on how perfectly the memory manager aligns the layout of the heap with the physical geometry of those hardware cache lines. Fortunately, the memory manager can anticipate data requests because executing code behaves predictably. Programs rarely sweep randomly through memory. They spend the vast majority of their time executing tight, repetitive loops over a small fraction of their data. This clustered, highly concentrated pattern of memory access is called locality. Look at this structure. When an algorithm repeatedly accesses the exact same memory location within a short window of time, the program is demonstrating temporal locality. Alternatively, programs exhibit spatial locality. Once a specific element is accessed, it is highly probable the code will immediately request the data sitting right next to it. Because the hardware strictly transfers data in those fixed-size cache lines, pulling the first node out of physical memory mechanically drags the adjacent spatial nodes into the cache right alongside it. If the memory manager groups logically related objects contiguously in the heap, it guarantees they will all transfer into the fastest cache tier simultaneously on the very first read. Exploiting spatial locality is not a theoretical optimization. It is an architectural requirement to prevent the processor from starving for data during intensive computations. Achieving perfect data locality is difficult because a long-running process continuously creates and destroys variables at unpredictable intervals. This factor represents the heap's available address space over time. As objects are continuously allocated and deallocated, the once contiguous free space degrades into an alternating sequence of used blocks and empty holes. If the aggregate free memory is totally sufficient, but no single continuous gap is large enough to satisfy an allocation request, the heap has entered a critical failure state, known as fragmentation. To mitigate this decay, the memory manager relies on precise algorithmic placement strategies. A naive first-fit algorithm simply drops a new object into the lowest address hole available. An optimized best-fit algorithm evaluates the geometry. BestFit scans the entire heap to find the absolute smallest available hole that is large enough to contain the requested memory chunk. By actively targeting the tightest possible match, BestFit statistically outperforms naive placement. It shields massive, continuous blocks of memory from being unnecessarily chopped up to satisfy tiny requests. These algorithmic placement policies act as mandatory survival mechanisms. Without them, an application will artificially exhaust its virtual address space long before the physical RAM is actually full. Of course, placement logic only dictates where new objects go. To keep the heap functional, the manager must aggressively identify unreachable data and return those chunks to the active free pool. Returning isolated chunks isn't enough. The system must merge adjacent free chunks together, a process called coalescing, to actively reverse fragmentation. Here is an isolated data chunk. To achieve coalescing in constant time, the memory manager invisibly injects metadata directly into the heap, specifically boundary tags at both ends of the chunk. Each tag stores a Boolean bit for its used or free status, along with an integer defining its total byte size. The moment a program triggers a deallocation request, the object's status bit simply flips from used to free. Instantly, the system reads the adjacent boundary tags to the immediate left and right, checking the physical status of its neighboring blocks. If a neighbor is also marked free, the background pointers update. The internal boundaries dissolve, and the outer tags recalculate their byte counts to represent a single, unified block of free space. By embedding these boundary tags directly into the data layout, the runtime system transforms the heap from a passive digital warehouse into an actively self-healing data structure. Languages like Java rely on automatic garbage collector to handle this deallocation cleanly, but in lower-level languages like C and C++, that automation is completely stripped away. The programmer is forced to manage the physical heap manually. This grid illustrates the first major failure mode of manual control, the memory leak. The program simply loses track of an object without deleting it. The manager continues operating, unaware the object is dead, slowly calcifying the available space until the system grinds to a halt. The second failure mode is far more destructive. A dangling pointer occurs when a chunk is explicitly freed, but a reference to its physical address remains active in the code. Watch the mechanics of a dangling pointer. A block is freed, and the manager reallocates that exact space to a totally new variable. Then the lingering pointer fires an update. It blindly writes to the old address, silently overwriting the new variable's data with its own payload and fatally corrupting system memory. Surviving manual heap management requires strict programmatic countermeasures. Developers enforce rigid object ownership conventions to guarantee only one pointer has the authority to delete an object, or they rely on dynamic instrumentation tools like Purify to catch illegal memory accesses as they happen. The abstraction of an infinite flat address space is a useful tool for writing code, but the heap is a deeply volatile physical environment. Mastering system performance means respecting the strict hardware limits hidden beneath every line of code.